All right, so welcome to Complex Analysis, Math 383. This is lecture 3. This is tentatively titled A Review of Real Analysis. You can ask questions on any classes which are supposed to be a prerequisite for this course. Abstract algebra is not fair game. You're welcome to ask, but I do have the right to say no to any questions asked in algebra. I have prepared some stuff on limsup, liminf from some questions some people had, and some stuff on Bolzano-Weierstrass, and I'm happy to talk about those. Is anybody interested in either of those topics? Okay, so let's quickly go through those. All right, so again, our game plan for today, limsup, liminf, convergence, and just talk about how to do all this stuff rigorously. And then if we have a chance at the end, talking a little bit about trying to sniff out equations. Anybody recognize the image on the right? I'm deliberately trying to do it so that you really can't see what's being labeled. Bunch of ship names. One of the most famous naval battles in the history of the world. Napoleonic times. I'm sorry? Battle of Trafalgar. And so if anybody's looking for a good math colloquium, mathematics of war, this is a phenomenal application. So Lord Horatio Nelson was the commander of the British forces, and he had his forces come in and split the combined Franco-Spanish Armada into two. This is a great example of divide and conquer. And so for a lot of what we're going to do, especially with Bolzano-Weierstrass, and throughout the semester, it's going to be this idea of divide and conquer, reduce, 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 keep reducing to something smaller, and work with that. All right. So here is, the math section is actually very good. This is a quick description of what is liminf, limsup. So basically liminf and limsup are what happens when you're in the unfortunate situation that the limits don't exist. So if you have a nice sequence that converges, then the limsup is the liminf is the limit. But not every sequence converges. Can somebody give me a sequence that doesn't converge? I'm sorry? Good. Sine of n is actually a really good one that doesn't converge. So why is sine of n, what's a really bad sequence that doesn't converge? No, negative 1 to the n is actually kind of similar to sine n.
1, 2, 3, 4.
1, 2, 3, 4, right? Because 1, 2, 3, 4 goes off to infinity. So there's no convergent subsequences in that sequence. Whereas, sine n and negative 1 to the n have very nice convergent subsequences. In fact, negative 1 to the n, it's very easy to see exactly what you should do to get the convergent. Basically just take all but finitely many of the terms have n, even all but finitely many of the terms have n odd, and you'll have something that converges. So limsup, liminf is what goes on when you don't have the limit existing. And so what they like to talk about is, there's lots of different ways of phrasing it. The way I kind of like it is, imagine we have a sequence xn, and then for each xn, we can look at what's going on, what's the largest number from that point onward. So here we're looking at the largest value from n onward. And then we take the smallest of all those largest numbers. Okay, so let's look at that in action. Let's say I give you an is 1 plus 2 to the negative n times negative 1 to the n. So when you look at this, does this sequence converge? Yes. And what is it going to converge to? So this converges to 1. Okay, I wish I knew how I got it to switch from red to black. Interesting. Okay, so it converges to 1. The color may change, but the value at least converges to 1. Okay, what if I give you a little bit more interesting? An is negative 1 to the n plus 2 to the minus n, negative 1 to the n. Does this converge? No. And so this basically is getting near 1 and negative 1. And so there's a whole slew of different types of sequences I can look at. And so for instance, if I imagine this is n, I'll be plotting a sub n up here. One possibility is I could have something, maybe it's coming down like this for a while. then it shoots up again, but it doesn't shoot up quite as high. Then it shoots up again, but it doesn't shoot up quite as high. Then it shoots up again, and it doesn't shoot up as high like that. Is this going to converge? So as long as it's going down by a fixed percentage, it will converge. And so let's just say, to make things painful, then the other ones are going to be on the other side down here. And so, again, we know it's not going to converge. And what we can do is we can look at, for any n, what is the largest value from that point onward. So if I specify over here, this would be the largest term from that point onward. If I move over a little bit to the right, maybe this becomes the largest, and then eventually this becomes the largest. And then eventually this becomes the largest. And I can look and see what happens to those. And that's going to be my limsup. My limsup is what's happening to these people over here. And that's going to converge. And now in a shaka, I can do the same thing down here and look at the ones that are the most negative. And then this would be the limit, and that will converge. So if I'm looking at the largest value from some point onward, as I go further down, could it ever get larger? Right? Because if I'm looking at the largest point from some point onward, well, the further I go to start, the fewer candidates I have. So I can never have things getting better. So when you go back and you look at this definition, I'm looking at the largest value from n onward. If I take a larger value of n, that larger value can only get smaller. So I have a sequence here that's clearly bounded from above, and it's decreasing or staying the same. And now we have some results from real analysis that say, if I have a sequence that's bounded from above and it's decreasing or staying the same, it either goes all the way down to negative infinity or it converges. And then in a shaka, if you just flip everything to the limit, now you're working upwards. And I have a sequence that's bounded from below. So this is the concept of the limit and the limsup. It's just a way to allow us to talk about sequences that do not necessarily converge. Out of curiosity, how many people remember the rearrangement theorem? Only one person remembers the rearrangement, 2 people? Okay, a few. So this is one of my favorite results. The Rearrangement theorem. So assume an converges conditionally, but not absolutely. Show can make the limsup, liminf, whatever you want. So at Princeton, back when I went there, they still had standards, and you had to demonstrate knowledge of at least 2 of French, German, and Russian. It did not mean you had to be able to speak it. It just meant you had to be able to read math in it, because there was a lot of math written in those languages that hadn't been translated. And so I was doing my German exam, which was an oral exam, and the professor just pulled a book off his shelf, opened it up, and I saw it was the rearrangement theorem. And in a flash of honesty, I asked him, do you want to see how good my German is, or do you want me to just quote the rearrangement theorem from memory, because I can tell that it's the rearrangement theorem? So let's see how good your German actually is. It wasn't great, but it was good enough to understand what was being made. And that's the level that you really need for a lot of this. You don't have to understand the flowery language and all that. You understand enough so that you can quickly read an article and get a sense of what's happening. To this day, I still occasionally have to read mathematical papers in French. There are some authors who are still publishing in certain areas in that. So the rearrangement theorem says if I have a sequence that's conditionally convergent but not absolutely convergent, I can rearrange the terms to have my limit and limsup whatever I want. So can somebody give me a series that converges conditionally but not absolutely? Alternating harmonic. So proof by example. Let's take -1 to the n over n. So we have -1, 1/2, -1/3, 1/4, negative a fifth. How much time do you have to know? Okay, so we have our alternating series. Somebody give me your favorite number, or a number that you're willing to publicly admit might be your favorite number. 7, good choice. I mean, 17 would have been better, but 7's fine. And I need another number. Other than 7. 3, okay. I just need to know which way to draw things. So here's 7, here's 3. And the way it works is we keep adding terms from the positives until we first exceed 7. So add positives till first exceed 7. Now what do we do? Yep, and then add negatives until we get just below 3. And now we do shampoo mathematics. Why is this shampoo mathematics? Louder, Vincent P. Louder, louder, please. Louder. I'm not sure if you're supposed to just repeat the lather and mince once, or if you repeat the whole thing, including the repeat. For those of you who know computer science, and hopefully get that. You just keep doing this. And so when you overshoot 7, will you overshoot 7 by more or less the next time? You sure? Because it could depend on just how things are. I'm not convinced that I will overshoot 7 by less the next time. But what I am convinced of is I will have a bound by how much I overshoot 7. And I know that bound is going to get smaller every single time because my positive numbers are getting smaller. So when I overshoot, what I'm using to overshoot is going to become smaller and smaller and smaller. So in the limit, I'm going to be overshooting 7 by less and less and less. And so I can arrange it so that my limsup will be 7 and my liminf will be 3. There's nothing special about 7 and 3. There's nothing special about the alternating harmonic. You can look at this and you can see I'm really not using too much about this. Maybe I'm using a little bit in this proof that my numbers are monotonically decreasing. And so if I give you a more general sequence, it might be a little bit hard. Yes?
What does it mean to converge conditionally?
So to converge conditionally means if I sum the terms in the order given, it converges. To converge absolutely means if I put in the absolute value, then it converges. And so there are a lot of functions that converge conditionally, but not absolutely, a lot of sequences and series. So as an exercise, I'm just popping another blank sheet. So converge conditionally, do in given order. Absolutely converges with absolute values. And so, for example, if I look at -1 to the n over n as my an, then the sum then goes from 1 to infinity of an. I can write that as -1 plus a half plus -1/3 plus a 4th plus -1/5 plus a 6th, and so on. And by looking at these terms, you can show that this sum is going to converge. And in fact, what's nice is when you write it like this, each new piece is negative, right? So if I stop after an even number of terms, what's left is negative. So I've overestimated the sum. And if instead I stop after an odd number of terms, I've underestimated. So it's really nice in terms of trying to understand what's going on. The general term, I'm going to have like a 1 over 2n minus 1 with a negative sign plus a 1 over 2n. So what do you get when you add them together? You get -2n plus 2n minus 1. So you would get -1 over 2n minus 1 times 2n. Right? So -1 over 2n minus 1, 2n, which is approximately negative 1 over 4n squared. And so if I look at the sum n goes from 1 to infinity of an. This is the same as the sum, say maybe m goes from 1 to infinity of negative 1 over 4m squared. And now this is, oops, I should technically write it as 2m minus 1 times 2m. And so now the question is just, how careful do you want me to be? Well, this is clearly approximately, the sum of 1 over 4m squared with the negative sign outside, and that's finite. If you want me to be a little bit more accurate, I could say, well, 1 over 2m minus 1 times 2m, this is less than equal to 1 over 2m minus 1 squared, and that's greater than equal to 1 over 2m squared. And so I can use that and then use some kind of like sandwich theorem from series to prove that things converge. So a lot of times as you go deeper in mathematics, you do less and less detail of the arguments, say, yeah, it's just going to converge. It's approximately this. I'm not going to bother and put in all the epsilons and the deltas. If you're ever unsure, by all means, put in all the epsilons and deltas. But it's essentially 1 over the squares. All right, so this is an example of something that's conditionally convergent. As long as we're here, this is a fun problem. Does there exist a continuous f such that the integral from 0 to infinity, and let's such that f of x is greater than or equal to 0, the integral of f of x dx is finite, the integral of f of x squared dx is finite, dot dot dot, the integral from 0 f of x to the 2020 is finite, but the integral from 0 to infinity of x to the 2021 dx is infinite. Yes. About the what? Yes. Right. So what I've shown is I have my, okay, so I should be a little bit more, I can make the limsup of the partial sums. Oh, it's not even right now. Okay. Of the partial sums. So when I form the series of partial sums, it's the limsup liminf of the partial sums that can be whatever I want. Well, again, what I'm doing here is it's not the original sequence, it's the sum of terms that if I rearrange them and I look at the sums.
Oh, so you rearrange.
I rearrange the sequence. I'm not adding it in this order anymore. So if I rearrange the sequence and then just add as I go and have that as my new sequence, I can have those sums alternating between 3. So basically, what this tells you is the order in which you sum terms matters when you have infinity. So if you think back to Fubini's theorem, when can you interchange the order of integration? It's if the integral of the absolute value is finite, then you can interchange the order. whenever you see an infinity, it's a danger sign. You have to be careful. And so what I will do is I'll just go first to Fubini. The integral over x, the integral over y of f, dy dx equals the integral over y, the integral over x, f dx dy, if the integral of the absolute value of x is finite. If the integral is not finite, you cannot always interchange orders. One of my favorite examples is, in the interest of time, I will not draw everything. And rather than doing a continuous example, I'll do a discrete example. And so I'm going to give you the value of my function or my sequence at these points. And so here's the point 0, 0, here's the point 1, 0, and so on. And I'm going to define my function, my sequence to be +1, -1, and then 0 for all eternity, 0, +1, -1, 0 for all eternity, 0, 0, +1, -1, and then 0 for all eternity. And I can look at the sum over m, sum over n of AMN versus the sum over n, sum over m of AMN. If I do the columns first, what does every column sum to? So column, then row gives 0. Row, then column gives what? 1. Because if I look at the row sums, the first row sum is 1, every other row sum is 0. So depending on how I add things, I can get a different answer. I'm sorry? Yes, it is. Right, because I haven't drawn everything. You know, in the interest of time, I could draw a few more, but right. And then just, you know, these continue. And so this is the simplest example I know of why you need the integral of the absolute value to be finite. That infinity means danger. Every time you see an infinity, you have to be careful about what's going on. And so if we have something like a series that converges conditionally, we need to be careful. This is why whenever we do things in complex analysis, we're always looking at these power series that converge absolutely in some disk. And if they converge absolutely in some disk, then we really don't have to worry about what's going on. You know, we can sum things in the order, everything is fine. We can rearrange them. But if things are conditionally convergent, then we have to be extremely careful. How many people did the rearrangement theorem in analysis? Okay, so it's a nice result. How about something like this? You know, does there exist a function that's continuous and non-negative, such that the integral of f squared all the way up to f to 2020 are all finite, but when you raise it to the 2021st power, it's infinite? Yes. So try f of x equals, what do you want to do?
X to the negative 20.
Are we okay when we start integrating at 0? What happens when you integrate this from like 0 to 1? So we have x to the negative 2022. When we integrate that, we've got x to the negative 2021. And then we plug that in at 0, we get 1 over 0, which is going to be infinity. So isn't this non-integrable?
No, I think you're right. I was thinking.
You can have 1 over x. And if you want it to be integrable near 0, you've got to make sure that the power is greater than -1. So try f of x is x plus 1 to the negative 2022? Well, the problem is when I integrate this, if I keep raising it to higher and higher powers, the function's getting smaller and smaller. Right? So this is not going to all of a sudden start to feel at 2021. You know, when I raise it to the 2021 power, that's going to be smaller than raising it to the 2020 power. So this also fails. You know, somehow my function has to be getting larger, right? So I need f of x to the 2021 to be greater than f of x to the 2020 somewhere. So I am a huge fan of Mark Twain. If you need a good quote, you know, go to Mark Twain. The one that I can use right now is roughly a cat that jumps on a lit stove will not jump on a lit stove again, nor will the cat jump on a cold one. You know, to each lesson in life, make sure you only extract the lesson you should. Be very careful. The key word is somewhere. I am not saying that f of x to the 2021 is always greater than f of x to the 2020. I'm just saying it's going to be greater than f of x to the 2020 somewhere, or there's no chance of this happening. So maybe there are some places where it gets really large and other places where it's small. Yes.
I can get started with discontinuous.
Oh yeah, discontinuous. I mean, when I say I want it to be continuous, I'm happy to just say I have something that's discontinuous and then tweak it.
So
Yeah.
basically, it's like one of the water functions in theory.
Okay.
So and you put like a rectangle of
Good.
width and the negative 20.2 and height n.
Good. So here's n, and then you're not drawn to scale. Here is n plus some little bit. How much should we move over? So 1 over n to the 2022, and then over here, it'll be n minus 1 over n to the 2022. And if you're not sure that it should be 2022, just put a delta over there as a free parameter, and then see what delta you need later. And then instead of using, you know, a bar function, if you want to make it continuous, you could use a triangle function. So you could use a triangle, or you could, you know, we'll do the bar. The bar is nice and simple. And I don't care that it's not continuous. We can always fix that. So we have something like this. And what's its height going to be?
N.
Height is n. And so now the integral is, you know, the integral from say 0 to infinity of f of x to the m dx is equal to the sum, and goes from let's say 1 to infinity, and we'll have n to the m, and then we're going to divide by n to the 2022, and I think we get to multiply by 2 because of the length. And so if m is less than 2020, it converges. If m equals 2021, it diverges. And if you don't like this, you know, the fact that it's not continuous, well, what you could do is you could just take the halfway point and then just have it come down linearly like that, and you'll be fine. And if you want to have it even continuously differentiable or infinitely differentiable, you could make that happen too. Yes.
I don't really understand what n.
Oh, this is just, you know, I'm defining my function f near the integers. So here's the real line. Here's the integer n. So near x equals n, f of x equals n. And it's a window of size 2 over n to the 2022. So I have a really small window about each integer. And near that window, my function gets very large. Is my function f bounded or unbounded? Unbounded, I have an infinity. You know, I have two sources of infinity. I have an infinite line, and I have a function that's unbounded. So function is unbounded. And that's the infinity that's responsible. So this is one of my favorite functions, one of my favorite examples of how bad real analysis can be. If I have a function that is integrable, what should be true about the function as you go further down the real line? What would you like to be true? Sorry? Yes, right? If the function is supposed to be integrable, it should be getting smaller as you go down the real line. It doesn't have to be. In Homage to Princess Bride, it has to be mostly decaying. Okay? It doesn't have to be decaying everywhere. It can have a couple of places where it's exploding, so long as it's exploding over smaller and smaller sets as you march further and further down. Something along those lines. The goal of today is to show you how hellish real analysis is. That we can have to deal with stuff like this. I'm watching my language because I don't want to have to say that this lecture is not appropriate for young children. We don't want to have to deal with this stuff. Complex analysis is much better. These strange, pesky things are not going to plague us. Okay. So the next thing I just want to briefly talk about is the Bolzano-Weierstrass theorem. How many of you have done this in real analysis? Okay. This is one of the most useful results we have. Basically, it says that if you have a sequence in a compact space, then it's got to have a convergent subsequence. And we will be using stuff like this all the time. And so I will give the proof in one dimension. And the proof that I like is the divide and conquer. So without loss of generality, the sequence AN lives inside the interval 0, 1. If it's bounded, you can always translate it and rescale so that it lives inside 0, 1. So what I can do is I can split into 0, 1/2 and 1/2, 1. And at least one of these has to have infinitely many terms. So if both of them have infinitely many, that's fine. At least one of them has infinitely many. So choose one of the sets that has infinitely many. Okay. And choose the smallest index that gives you a point in that set. And that will be your A sub n1. Smallest index in the subinterval with infinitely many terms. And now it's shampoo again. We just repeat. And so now what we would do is now we would look at 1/2 to 3/4, and then 3/4 to 1. And one of those would have to have infinitely many. So if initially this was the one that had infinitely many, now assume maybe it is this one that has infinitely many. And when you choose the smallest index, AN2, that's in there. And we continue. Will this give us a sequence that converges? Have we finished the proof? Okay, why not? So it's a question of what level of rigor do you need? One of my good friends left math for engineering after, in our advanced freshman math class at Yale. He thought he was done because he was trying to prove by contradiction, and he proved that the answer was an integer and the answer was 1/2. And the grade about, well, how do you know 1/2 is not an integer? And at that point, he became a chemical engineer and said, I'm done. So what's going on here? What do we have? So we have our terms, AN1, AN2. AN3, AN4, ... Each in I1 contained in I2 contained in I3. So we have a sequence of intervals And the length of in is equal to twice the length of in plus 1. Or maybe we'll do in. So if you think about what's going on, we have ln1 less than equal to an1 less than equal to un1, where I1 is the lower bound, upper bound. And then we would have ln2 less than equal to an2 less than equal to un2, where I2 is the lower and the upper. What do we know about the lower bound n2 versus the lower bound n1? It can't be low. So we know it has to be like this. What about un1 and un2? So we know the lower bound of the second interval can't be smaller than the lower bound of the first. What about the upper bound of the second to the upper bound of the first? This small is less than equal to. So the lower bounds are going like this. The upper bounds are going like this. Do they converge to a common point? Why? Yeah, the distance between them is going to 0 because each interval is half the size of the previous. So what we're basically trying to say is, we have a sequence of compact sets. We're looking essentially at their intersection. And because the length of each is half of the previous, the intersection is going to just be one point. The question becomes, how much detail do you want to do for something like this? Converge to same point. And so if they're converging to the same point, what theorem do we then use to show that the ANs converge to that point? Squeeze theorem or the sandwich theorem. So squeeze or sandwich theorem gives the A and K converge to the intersection of the I and Ks, which is just a unique point. I'll call it X star. Yes.
I'm not sure I understand our process at the beginning where you cut it in half and then which one do you choose?
Well, because I have infinitely many points in my sequence, either the first half, the second half, or both have to have infinitely many terms of the sequence. And so, if they both have infinitely many, maybe you just always take the one on the left.
So it is, but it is possible.
It is absolutely possible that they both have. And so it's absolutely essential that we have infinitely many terms in the process. And as long as we have infinitely many terms, one of the intervals has to have infinitely many. And so we can keep going. Yes.
Yeah. I'm not sure what this proof is to do with compactness.
Well, we're assuming that AN lives in a closed compact set.
So you just generalize.
Right. I'm just doing the special case in the real line. Where am I using closed? Yeah, but where am I using closed?
Well, if you have open set, then you could use increasing equals closed set.
Well, let's see. For the subintervals we have.
Yeah, but if you didn't have 0 or 1 in the set.
So if we didn't have 0, 1 in the set, that's where the problem is. Is that it's that very far left end point or that very far right end point. If that's where the action is, then we're in trouble. Is it, we need it to converge. It depends on how you write things. This says that every bounded sequence has a convergent subsequence. And so the question, converge in that space or whatnot. And so it's still converging, it's just not converging into the open interval 0, 1. So it's you can play around with it a little bit in terms of how you want to phrase it. You often want to have a closed boundary so it's converging in your space. Right, and then I only look at indices that are now larger than that.
Okay.
And so from this point onward, we only look at terms larger than that.
So you're splitting up that interval too, but you're doing the same.
Right, so let's say 77 is the first index that's in here, and I have infinitely many. So now I only look at 78 and on. And then if this is 2015, I would then only look at 2016 on after that. So when we split, we only look at indices that are larger from that point on. And then that way the sequence will come into order. So it's, it's always a question of how much detail do you want to put in. If you read math research papers, you see that there's very little detail. And a lot of times there are results that people use that are not in the literature at all. I remember I was working on a paper years ago on elliptic curves with a colleague of mine, and I'd been, I'd known him for years. I was his mentor. I've now mentored some of his students, and we needed a result, and we proved it, but we felt that it's got to be in the literature. So we asked his advisor, who was, one of the experts. Oh yeah, this is well known. We thought so. Could you give us a source? No. Everybody knows it. And so there's a lot of things like that it's just everybody knows, but you can't find it anywhere. And so if you want to be complete, you actually should include a proof of that. And maybe you have that as an appendix and you leave it on the archive and you don't have that in the published journal article. I'm happy to talk to people about, sadly, what needs to be done to make journals happy when you submit papers. We do not write math papers in a friendly manner. A lot of people feel that if you put in too much detail, people are going to think that the paper isn't that deep. But it's the detail that's often absolutely necessary because you can make a very small calculation error that invalidates everyone. So the question is, how much detail and how much rigor should I be doing for something like this? Is a sketch like this enough detail, or do I really need to open it up and put in more? I hope that something like this is enough, to give you a sense of what's going on. I've got my intervals, I've got my lower bounds, my upper bounds, I'm sandwiching in, they have to converge to a common point. Why? Well, the lower bounds have to converge to something. Why? Bounded, it's bounded from above. And the upper bounds have to converge because they're bounded from below. And if the lower and the upper bounds don't converge to the same point, well, then you have a gap. And we know that eventually the size of all of our intervals is smaller than any number because each one is half the size of the previous. So that's the rigorous proof that they have to converge. On an exam, what should you do? And after you cry? Cry some more. So you should provide full details on an exam. On an exam, you have to view me as an idiot who can understand correct answers when given, but other than that, I have no math knowledge. If you are unsure if you need to prove something, what should you do? Ask, right? What's the worst thing that will happen? You'll have to prove it, right? I'm not going to say you've now flunked the course for asking that. I'm not going to go after you and your family, right? If worst cases, I'll say, prove it. All right. Any other questions on Bolzano viruses? This is your great idea of divide and conquer. Is take a hard problem, keep splitting it up into small things, and this idea of repeating, bringing things down to smaller and smaller scales. We're going to be doing this all the time when we start proving our results from complex analysis. All right, so on the page over here, there is an equation in the upper right corner. Anybody know what equation that is? Yes, Schrodinger's equation. I would be shocked if you know why Schrodinger's equation is here. Okay, be careful, this is being recorded. When I was an undergraduate, I took a class in quantum mechanics. And unfortunately, we didn't get to the Schrodinger equation because we spent the first 2 weeks of class reviewing linear algebra, which was a prerequisite for the course. Now, by reviewing linear algebra, what's the gain? What's the benefit of spending 2 weeks reviewing linear algebra? Yeah, is that hopefully this will help people understand things a little bit better. Unfortunately, there is only a finite amount of time. And so the more time you spend reviewing things, the less time you have to do new things. My daughter has made some remarks in frustration about what's going on in her class, that, why are we reviewing what we just did last year? We should be moving on to new stuff. Yes. So I am not going to spend too much time reviewing real analysis. We do have graders, we have myself, you are happy to have you come and ask me questions, happy to have you talk with each other, with the TAs. The other thing is I am willing to adjust a little bit of class time. And so if review sessions like this are useful, what I'm quite happy to do is say, well, look, today I'm not going to cover the material, just watch the video from 2017, and we'll just make today another just general review class because it is valuable. I mean, there is a value to spending 2 weeks reviewing linear algebra. A lot of people, when you're learning the material, you don't necessarily understand why are we learning this. In my probability class, I asked my students, why do we study logarithms? And the answer I mostly got was, well, that was in the curriculum. And there's plenty of things you can put in the curriculum. My first year here, I remember my TA being amazed when we were discussing what I wanted to do in Calc 1. Wait, you have a choice? Yes, you get to choose which parts you want to do. How many of you did curve sketching in high school? Okay. If you did curve sketching, how many of you did not do high school in America? Okay, I was curious to see how many of the people who did it is from another country in terms of their philosophy. How many of you learned how to use sine tables, cosine tables, log tables? There's certain things that we no longer really teach, right? Why don't you have to learn how to use these tables anymore? Yeah, you've got calculators, you have the internet. So as things change, we have the ability to reallocate what material we cover. And what is the trade-off? Table of integrals used to be very hard to use because there's so many different equivalent formulations that the difficulty was, how do I convert what I have to match in front of me? And in fact, my physics professor told us you had to have 2 table of integrals, the big monster at home and the small portable one to have on you at all times. If I remember, I will try to bring a slide ruler to class in the near future. I actually have 2 different types, the standard as well as the circular. Circular is much better. All right, so if people do want to have more just general reviews, I'm happy to do that and reallocate classes. So Friday is going to be a flipped lecture, just so we have a last of the different possibilities. So I will have you watch the video beforehand, and then I will discuss whatever you want to discuss from that. All right.